Good evening, everyone. Let's just wait for 5 minutes so that everyone can join. So I hope you You all must have gone through the lecture videos, and today we'll be solving some wave equations again using for different cases the finite string and the infinite string, as we had done in the last session as well. Here we will be dealing with some different kind of boundary initial conditions. So let's start. I hope my screen is visible now. So let's start with something that we had done earlier as well. A wave equation on of a wave equation for a finite string with some boundary initial boundary conditions. Question number 1. Find the solution of the initial boundary value problem u t t minus c square uxx is equal to 0 for all x belonging to 0 to L t positive. That means we have a finite string of length L with some initial boundary conditions ux0 equals to 1 by 4 x1 minus x, sorry, L minus x, ut at x0, that means the initial velocity is 0, that means the string is at rest, and its position at time t equals to 0 is similar to the curve of x 1 by 4 times x L minus x. So this is for all x in 0 to L. Then we have u0t is equal to 0 is equal to ult. That means the string is fixed from both the ends for all t positive. Let's mark this as star. So we will be solving it using the separation of variable method. Let uxt is equal to xx dt. This implies utxt is xx t dash t, uttxt is equal to xx t double dash t. Similarly, we have partial derivative with respect to x. It will be complete derivative of x times t as it is because it is independent of x. Similarly, uxx will be x double derivative and t as it is. Now we have some initial conditions. U0 t equals to 0 by star. We have 0 is equal to u0 comma t, which is x at 0, t at t, and this is for all t positive. This implies that x0 must be 0 because if t is a trivial function, tt is 0 for all t, that would give us a trivial solution. That is not what we want. We are searching for non-trivial solution. Similarly, we have 0 equals to u0 ult, lt, which is equal to x at l dt for every t positive, and again this will imply that x at l is 0. Third condition is ut at x0 equals to 0. 0 is equal to ut x0, which is ut is x at 0 t dash t. X at x t dash 0 for every x belonging to closed interval 0 to L. This will imply t dash 0 is 0, because again x should not be a trivial function. Now putting the values of utt and uxx in the equation utt minus c square uxx equals to 0, we will get t double dash t times xx minus c square x double dash x tt is equal to 0. This will give us x double dash x by x is equal to t double dash t by c square t. Now we can see that on one side of the equation we have a function of x, whereas on the other side we have a function of t, and they both are equal. This can be possible only if it is a constant, because on either side we have two different functions depending on two different variables. They are equal for all x and for all t. That can happen only if this is equal to some constant lambda. So let's mark this as 1, 2, 3, 4. So by 4, we have x double dash x minus lambda xx is equal to 0. Now this is a second order homogeneous linear differential equation. We can solve it by finding the auxiliary equation. So here its auxiliary equation is r square minus lambda equals to 0, which implies r square is equal to lambda. Now we'll see what happens for different cases of lambda when lambda is positive, lambda is 0, and lambda negative. So we have case 1 when lambda is 0. In this case we get r equals to 0, 0, which implies x is equal to c1 plus c2x. Now by first and second we have 0 equals to x at 0. X at 0 is c1. So c1 must be 0. This implies x is just c2x. Now again we have 0 equals to x at L, which is c2L at c2 times L. Now since L is non-zero, we must have c2 equals to 0, which implies x is a trivial function. That is not what we want. Now this will imply that uxt is 0. Next we will see what happens for the case lambda positive. That is lambda is equal to k square for some k positive. Sorry, k non-zero. Can be negative also because its square will anyways be positive. So taking lambda equals to k square, we get r is equal to plus minus k. In that case, we know that x will be c1 e to the power kx plus c2 e to the power minus kx. Now by first and second we have x at 0 is 0. That means c1 plus c2 is 0. That is c1 is equal to minus c2. This gives us x at x is equal to, if we take out c2, so we'll get minus e to the power kx plus e to the power minus kx. So also we have x at L equals to 0. So 0 is equal to x at L, which is c2 e to the power minus kl plus, minus e to the power kl. This must implies that c2 is 0, because e to the power kl is never equals to minus e to the power minus kl, because that would imply that e to the power 2kl is 0, which does not happen ever, because we all know that exponential function never attains 0. So this will imply again that x is a trivial function, which will imply that u is a trivial solution. These cases we are not getting any non-trivial solution. So let's see what happens for the case lambda equals to lambda negative. Case 3, when lambda is negative. That is lambda is equal to minus k square for some k non-zero. And this will imply that r is equal to plus minus k iota. This implies that x is equal to c1 cos kx plus c2 sin kx. Now by the initial conditions, by first and second, we get 0 is equal to x at 0 is equal to c1. This implies x is just c2 sin kx, and 0 is equal to x at L, which is equal to c2 sin kl. Now we want c2 to be non-zero, otherwise again we'll get a zero solution and we are left with nothing. So for c2 to be non-zero, this implies we must have kl equals to n pi, because in that case sin kl will be 0. That is k should be equal to n pi by n. Now since this is depending on the natural number n, we'll write it as k. This implies for lambda n equals to minus n pi by l square, we have a non-trivial x n x, which is equal to cn sine n pi by l x. Now we have got x. Now we'll find t. Again by equation 4th, we have tn double dash minus lambda c square tn lambda n tn equals to 0. Since for every natural number, moreover for every n1 to infinity, we can find different xn, so we will search for different tn. That is why I just replace the t by tn. Now so its auxiliary equation is r square equals to lambda n c square, which is minus n pi by l c whole square. Now in this case, we know that t in t is equal to sum a n times cos n pi c by l t plus b n times sin n pi c by l t. Now we had some initial condition for t. By equation third, we have t dash 0 equals to 0. By third, we have 0 equals to tn dash at 0, which is basically, so since the derivative of since the derivative of cos x is sin x, and sine is 0 at 0, so this first term will vanish. We'll be left with the second term, which is bn n pi c by l times cos n pi c by l t, because the derivative of sine x is cos x. Hmm. Um, Now since n pi c by l is non-zero, or sorry, after putting t equals to 0, so this is just 1. Now since n pi c by l is non-zero, we have bn equals to 0 for every n in n. Not just n. This implies t is just an cos n pi c by l times t. Now we have Tn and Xn. So by the principle of superposition, we get uxt is equal to summation n from 1 to infinity. We'll take some other constant dn, which is just an times cn sine n pi x by l, sine n pi x by l times cos n pi c by l t. So now till now we have used the three boundary conditions, initial boundary conditions that we were provided. So we haven't used the first one, ux 0 equals to some function of x. So let's use that. So by star, we have 1 by 4 x l minus x is equal to u at x comma 0. So since cos 0 is 1, we have summation n from 1 to infinity dn sine n pi x by n for every x n 0 to n. From here, we know that we can find these coefficients dn, and they are given by dn is equal to integration 0 to l 1 by 4 x l minus x times sine n pi x by l dx by integration 0 to l sine square n pi x by l dx. Now you can easily evaluate, and I think we did it in last class, that this integral will be L by 2. So we are left with 1 by 4 0 to L Lx minus x square sine n pi x by L dx. So we'll be using integration by parts to integrate it. So this will give us, this is 1 by 4 Lx minus x square as it is. Integration of sine x is minus cos n pi x by L by n pi L 0 to L minus integration 0 to L. The derivative of first term is L minus 2x times integration of sine n pi x by L, that is minus cos n pi x by L by n pi times L dx. Now you can see that here when you'll put x equals to L, we'll get L square minus L square, that will give us 0, and at x equals to 0 also this term will vanish out. So this is equal to L by 4 n pi integration 0 to L minus 2x cos n pi x by L dx. So we'll be using integration by parts. So this will give us L by 4 n pi L minus 2x as it is. Integration of cos x is sin x, so this will be sin n pi x by L by n pi times L 0 to L minus integration 0 to L. Derivative of the first term will give us minus 2, and integration of cos is sin n pi x by L by n pi times L dx. Now since sin n pi is 0, sin 0 is 0, this first term will vanish out. So we'll be left with L 4 n pi, or uh, we'll be left with 2L square by 4 n square pi square integration 0 to L sin n pi x by L dx, which is nothing but L 1 by 2 times L by n pi whole square. Integration of sine is minus cos n pi x by L by n pi times L 0 to L. So this is minus L cube by 2 n cube pi cube. You know that cos n pi is minus 1 to the power n and cos 0 is 1. So this is L cube 1 minus 1 to the power n by 2 n cube pi cube, which is 0 when n is even, because when n is even minus 1 to the power n will be 1, and this will turn out to be 0. And for odd, this will be 1 minus 1, that will be 2, and this 2 will get cancelled out. We'll be left with L cube by n cube pi cube when n is odd. So this implies dn is equal to, so we'll have to divide it by L by 2. Because the denominator integral is L by 2. So this is 0 when n is even, 2L cube by L n cube pi cube when n is odd. Or we can directly write it as L square. This implies uxt is equal to summation k from 1 to infinity. So we'll be taking just the odd term. So we'll replace n by 2k minus 1. This is 2L square by 2k minus 1 cube pi cube. The rest of the terms will be same. Sin n pi x by L, sin n pi x by L times cos n pi c by L t. I hope this solution was fine with everyone. I have tried to go through all the details so that you get good idea about the solution, how the terms are coming. Uh, I would like you to go through the solution once again, and if you have any doubt, please let me know. Let's move to the next question. We'll do one more question of the similar type. This time I will not be going into details that much. I hope I have given enough of the details so you can do yourself the other questions. Let's try. Question number 2. Find the solution of the following initial boundary value problem. UTT minus C square. Let's write it. UTT minus C square UXX is equal to 0 for 0 less than x less than pi and t positive. With the initial boundary conditions, ux0 is equal to 0, ut at x0 is sine x, for all 0 less than x less than pi, u0 comma t is equal to 0, which is equal to 0 at pi t. That means we have a finite string of length pi. Initially it is at rest. It is tied fixed at both the ends, and at time t equals to 0 it is not at rest. In fact, its motion is can be expressed by the function sin x. So let's mark this as star. Again, we'll be using separation of variables to solve this. So this time I'll write directly. Let uxt is equal to xx From here we will get x double dash x by xx is equal to t double dash t by c square times tt. That must be equal to lambda. So we'll number this 1. And by the initial conditions, we have 0 is equal to ux0, which is xx t0 for every x. That will give us t0 is 0. I will mark it as number 2. Then 0 is equal to u0t, which is x0 tt for every t. This will imply that x at 0 is 0. I'll mark it as number 3. And 0 is equal to u pi t x pi tt for every t. That must imply that x at pi is equal to 0. So by first, we will again have two differential equations in variable x and t. By first, we have x double dash x minus lambda times x is equal to 0. So this is again a second order homogeneous linear differential equation. So it can be solved by using auxiliary equation. Its auxiliary equation is r square is equal to lambda. So again we'll have three cases. I'll not go into the details. Again, for lambda equals to 0, by third and fourth we will get x is trivially 0. You can do it yourself as we had done in the previous question. Case 2, when lambda is positive, again by third and fourth we will get x trivial solution, which will imply that uxt is 0. Case 3, lambda is negative. I will take lambda to be minus k square for some k non-zero. That will give us r is equal to plus minus k iota, and hence xx is equal to c1 times cos kx plus c2 times sin kx. Now by third we have 0 equals to x at 0, which is c1. This implies xx is just c2 times sin kx. And by fourth we have 0 equals to x at pi, which is c2 sin k pi. Now this will be 0. Now we want C2 to be non-zero, because if C2 is 0, again we'll end up with a trivial solution. For C2 to be non-zero, we must have K equals to N. That means for lambda N equals to minus N square, we have xnx is equal to some Cn times sine nx. These lambda n's are called eigenvalues and corresponding xn are called eigenfunctions. I hope you remember we did some eigenvalue and eigenfunction questions in previous sessions. Also, by equation first, we have Tn double dash minus c square lambda n Tn is equal to 0. So its auxiliary equation is r square is equal to c square times lambda n. So lambda n is minus n square. So this is minus nc square. So this will give us Tnt is equal to an cos nct plus some constant bn times sine cnt. So we have one initial condition for t as well. T0 is 0. This gives us 0 is equal to T0, which is equal to, since cos 0 is 1 and sin 0 is 0, we have n equals to 0 for every n. This gives us Tnt is just Bn sin nct. Therefore, by the principle of superposition, we have uxt is equal to summation n from 1 to infinity. We'll take some other constant dn, which is just bn times cn sine nx times sine nct. Now till now we have not used one initial condition, that is utx0. So we have by star we have sine x is equal to utx0, which is equal to summation n from 1 to infinity dn. Since derivative of sine x is cos x and cos x 0 is 1, so we have this is equal to n dn c sine nx. Now we know how to find these coefficients dn. N c dn is nothing but integration 0 to pi sine nx sine x dx by 0 to pi sine square nx dx. We all know that this denominator is 0 to pi sine square nx dx is equal to pi by 2. Moreover, you can evaluate it that sine nx times sine x by using basic identities of trigonometry. This must be 0 for all n not equal to 1. And for n equals to 1, it is again integration 0 to pi sine square nx, sine square x. Sine So it will be integration 0 to pi sine square x. That will be just pi by 2. So therefore, NCDN is equal to 0 for all n not equal to 1, pi by 2 for n equals to 1. This implies D1 is nothing just but pi by 2c, and Dn is 0 for every n not equal to 1, which implies uxt is just sine x sine ct times pi by 2c. Sine x sine ct. I hope this solution was fine with everyone. I would like you to go through the solution once again, so that if you have any doubt, you can just go through it again. And if you have any doubt, please let me know. So this dn, to find this dn, we need to divide this term by pi by 2 as well. So this will be 1, and hence d1 will be just 1 by c. So I'm sorry about this silly mistake. 1 by c, this is by c. I hope you got what was the mistake, because NCN is this numerator upon denominator. I was not dividing it with the denominator to find the coefficient dn. Yes, see, that's why we should always go through the solution once again. There might be some mistakes because we are doing so many things at a time. We might leave out some things that we think are trivial, but they are not. They are affecting our solution, na? So I'll just wait for you. Let's move to the next question. Next, we'll see a problem related to the infinite length string. There we won't be using the method of separation of variables. Instead, we'll be doing some substitution. Question number 3. The vertical displacement uxt of an infinitely long string is determined from the initial value problem utt is equal to minus infinity to infinity t positive with some initial condition ux0 equals to fx and ut, that means the initial position is given by function fx and initial velocity is given by function gx. We'll mark this as star. So this problem can be solved without separation of variables. Can be solved without separation of variables. First part, so that the wave equation can be put into the form so that the equation star can be put into the form u eta zeta equals to 0, where eta is equal to x plus ct and zeta is equal to x minus ct. And the B part, integrate the partial differential equation in first. Integrate the PDE we got in part A first with respect to eta and then with respect to zeta to show that uxt is equal to some function fx plus ct plus some other function g of x minus ct, where f and g are some arbitrarily twice differentiable functions. Where f and g are arbitrary twice evaluate the expression for f, g and hence u. You can see that a lot of hint is already given in this in this problem. So for the first part, we'll start with the substitution eta equals to x plus ct and zeta equals to x minus ct. From that, we need to deduce that the problem u dt equals to c square u xx can be transformed to u eta zeta equals to 0. So let's start with it. Solution. A part, let eta equals to x plus ct and zeta equals to x minus ct. So this gives us u eta is equal to ux, sorry, ux is equal to u eta plus u zeta, and which implies uxx is equal to u eta eta plus 2u zeta eta plus 2u eta eta. I would like you to go through the earlier sessions where we had done a lot of problems related to such substitution. You'll easily get to know what we are doing here. Similarly, we have ut equals to c times u eta minus c times u zeta, and this will imply that utt is equal to c square times u eta eta plus u zeta zeta minus 2 u eta zeta. Now, since we have 0 equals to ux utt minus c square uxx, substituting the values of uxx and utt in this equation, we get this is equal to, taking c square to be common, u eta eta plus u zeta zeta minus 2u eta zeta minus u eta eta minus 2u zeta eta, or let's write it as u eta zeta minus u eta eta. So these terms gets cancelled out. Oh my god. See, this is here zeta zeta. So this gets cancelled out. We are left with minus 4u eta zeta c square is equal to 0. Now since 4 is non-zero, c square is non-zero, we are left with u eta zeta is equal to 0. This is what is asked in part A. Now the B part says that we need to integrate the equation firstly with respect to eta and then zeta. Let's start with this B part. So from here we have del by del eta del u by del zeta is equal to 0. Now integrating with respect to eta, therefore we get the derivative of del u by del zeta with respect to eta is 0. This tells us that del u by del zeta is basically independent of the variable eta. That means it is some function of zeta. So del u by del zeta is nothing but some function of zeta, because in that case only its derivative with respect to eta will be 0. And again integrating with respect to zeta. Now after integrating g1, we will get some other function g. So we get, and along with that we will have, instead of arbitrary constant, we will have an arbitrary function that will depend completely on eta, because it's again its derivative with respect to zeta will be 0. So u zeta eta is equal to g zeta plus some function f of eta, or writing it in terms of equivalent t, we have f eta was x plus ct, x plus ct plus g of x minus ct. So this is what we wanted to show. Further, where clearly here f and g are arbitrary twice differentiable functions. Further, we need to find the expression for f, g and u. For that, we will be using the initial conditions that we are provided with. So we have two initial conditions: u at x comma 0, that means at time t equals to 0, and ut at x comma 0. So by star, we have fx is equal to u at x comma 0, which is fx plus gx. Therefore, we have fx plus gx is equal to small fx. Moreover, this will give us f dash x by g dash x is equal to f dash x. Now let's number this as equation. Let's number this as 1, this as 2. Moreover, we have gx is equal to u t at x comma 0. Now see that derivative of u with respect to t is c times f dash at x plus ct. Putting t equals to 0, we will be left with f dash x minus c times g dash at x minus ct. Putting t equals to 0, will be left with gx. Now this will give us f dash x minus g dash x is equal to gx by c. Let's number this one as third. So we can see that second and third are two linear equations in f dash and g dash. We can directly solve them by basic elimination method. By second and third, we have, you can see, we will get f dash x equal to f dash x by 2 plus gx by 2c by adding equation second and third. So integrating both the sides from 0 to x, we will get f x minus f at 0 is equal to fx minus f0 by 2 plus integration 0 to x gs ds. Now this gives us fx is equal to fx by 2 plus 1 by 2c 0 to x gs ds plus f0 by 2 plus capital F0. And by equation third, we will get g dash x is equal to f dash x minus gx by c. F dash x minus gx by c. Now what is f dash? F dash is f dash x by 2 plus gx by 2c minus gx by 2c. Gx by c, which is f dash x by 2 plus gx by 2c. Now again integrating both the sides from 0 to x, we will get g dash x, sorry, gx is equal to fx by 2 plus 1 by 2c integration 0 to x g s ds. So this will be a minus here, plus g0 minus f0 by 2. So if I mark this one as hash or hash 1, this one as hash 2, by hash 1 and hash 2, we get uxt. Now uxt was fx plus ct plus gx minus ct. So this is fx plus ct plus fx minus ct by 2 plus 1 by 2c integration 0 to x plus ct gs ds plus 1 by 2c integration 0 to x minus ct gs ds along with some constants f0 plus g0 minus f0. Now by equation by equation first, we know that capital Fx plus capital Gx is equal to small fx for every x. That means f0 plus g0 will be equal to small f0. So this is 0. By first, we have f0 is equal to f0 plus g0. Therefore, uxt is just fx plus ct plus fx minus ct by 2 plus integration 0 to x plus ct gs ds plus integration 0 to x minus ct gs ds by 2c. So this is the expression for our solution. I hope this solution was fine with everyone. If you have any doubt, please let me know. I can explain it again. I've tried my best to give all the details that we require. So in the next question, we will find this solution for some specific given fx and gx. So I'll just wait for 5 minutes so that if you have any doubt, you can let me know. Question number 4. Find the solution of question number 3 for a, fx equals to sin x and gx equals to 1. B part, fx equals to sin x, gx equals to cos x. So here we'll have to use basic trigonometric identities. So this gives us f ct plus fx minus ct by 2 is equal to 1 by 2 sin x plus ct plus sin x minus ct. We know that sin a plus b is 2 sin a plus b by 2 times cos a minus b by 2. So this is equal to 1 by 2 times 2 sin x plus ct plus x minus ct will give us 2x by 2 will give us just x, and cos x plus ct minus x plus ct will give us 2ct by 2, that means ct. So this is just sin x cos ct, and the other term is integration 0 to ctg. So since gx is just 1, 0 to x plus ct ds plus 0 to x minus ct ds is nothing but x plus ct plus x minus ct is by 2c is just x by c. This gets cancelled out. Therefore, uxt is sin x cos ct plus x by c. So in B part again fx is same, so fx plus ct plus fx minus ct by 2 will be same, sin x cos ct. We will have to evaluate the integral of g. So in B part gx is cos x, so 0 to x plus ct, gs dx is integration 0 to x plus ct cos x dx, and integration cos x is sin x sin s s s s 0 to x plus ct. So this is again sin x plus ct, and similarly we will get 0 to x minus ct gs ds is equal to 0 to x minus ct cos s ds is equal to sin s 0 to x minus ct. This is nothing but sine x minus ct, because sine 0 is 0. So from here, our solution uxt is equal to fx plus ct plus fx minus ct by 2, that is again sin x plus sin x times cos ct. This is sin x cos ct plus sin x plus ct plus sin x minus ct by 2c. So again we will be using sin a plus b. So as done earlier, we will again get 2 sin x cos ct. So this is nothing but 1 plus 1 by c times sin x cos ct. Let's do one more problem related to finite length string. This time we will be having a little bit difficult kind of initial conditions. Let's see how. Question number, so this is question number 5. Difficult in a sense. Till now we were having three terms to be zero. From there we would easily simplify our solution, but in this case some initial conditions would be non-zero. Let's see the problem. Question number 5. Find the solution of the, wait a second, of the initial boundary value problem minus c square uxx is equal to 0 for all 0 less than x less than 1, t positive. We are given that ux0 is equal to some function of x. Also ut at x0, so at time t equals to 0, nothing is at rest. We have some displacement, all, and as well as the string is not at its, we can say, the position of equilibrium. And yes, the string is tied on both the ends, so we still have this condition. This is for all 0 less than x less than 1, and this is for all t positive. So now I would like you to start solving this, because again we will start with the with taking x uxt to be xx and tt. From here we will get again x double dash by x is equal to t double dash by c square t, that should be equal to some lambda, along with the boundary some initial conditions from, let's mark this as star, from the fact that u0t is 0 and u1t is 0 for all t. We will again have the same conditions, initial conditions. I would like you to see all the cases for lambda. See that for lambda greater than equals to 0, we will have just the trivial solution, and the non-trivial solution can be found for lambda n equals to minus n pi square, and for that xn x will be cn sine n pi x. So please do till here. After that we will find t. So in order to find t, now we don't have any condition on t that is 0. So just do till here. Uh, So I hope you all can deduce that this xn will be cn sine n pi x and lambda n will be minus n pi square. So let's number this as 1. By first we have Tn double dash minus lambda c squared Tn equals to 0. This is again a second order homogeneous linear differential equation. Its solution can be we can find its solution using the auxiliary equation. Its auxiliary equation is r square is equal to lambda c square. So lambda n is minus n pi times c square. So this gives us TNT is C A n times sine n pi ct plus some constant Bn times cos n pi ct. Now this time neither an nor bn are 0. So by the method of principle of superposition, from here we will get by the principle of superposition we get uxt is equal to summation n from 1 to infinity. We will write some other constants dn sine n pi ct plus en cos n pi ct times sine n pi cx. So this is our general solution. Now this time we need to find the coefficients dn as well as en. So for that we have two conditions, two initial conditions. We know that by star we have x1 minus x is equal to u at x comma 0. So putting t equals to 0, since sine 0 is 0 and cos 0 is 1, we are left with summation n from 1 to infinity en sine n pi cx. So from here en is integration 0 to 1 x1 minus 1 minus x times sine n pi c x dx by integration 0 to 1 sine square n pi c x dx. Also we have x1 minus x is equal to ut at x comma 0, which is equal to since sine n pi x is independent of t, we have summation n from 1 to infinity. Derivative of sine x is cos x and cos 0 is 1. So we have dn n pi c cos 0 plus derivative of cos x is cos t is sine t minus sine t, and sine equals to 0. This will be 0 times this is independent of x sine n pi x n pi c x. So that means we have x1 minus x is equal to summation n from 1 to infinity n pi c dn sine n pi c x. From here we know that we can evaluate these coefficients n pi c dn is equal to integration 0 to 1 x1 minus x times sine n pi c x dx by 0 to 1 sine squares n pi cx dx. Thankfully, in both the cases, we need to evaluate the same integral. We know that this denominator is sine square n pi cx dx. You can evaluate. This will turn out to be 1 by 2. Now all we need to evaluate is the integral 0 to 1 x1 minus x sine n pi cx dx. Again, we'll be using integration by parts. So this is x minus x square as it is. Integration of sine is minus cos n pi cx by n pi c 0 to 1 minus integration 0 to 1. Derivative of x minus x square is 1 minus 2x minus cos n pi c x by n pi c dx. Now putting x equals to 1 and 0, the first term will vanish out. We will be left with 1 by n pi c. So let's integrate the second term. 1 minus 2x as this. Integration of cos x is sin x. So this is sin n pi cx by n pi c 0 to 1 minus integration 0 to 1 minus 2 sin n pi cx by n pi c dx. Now since sin n pi, we have n pi c. Wait a second. I don't have c with x. Oh, I'm so sorry. So here we don't have c. This is just x. So we don't have c here, here. N pi x, n pi x. Similarly here. This is n pi x, n pi x, n pi x, n pi x. Also, yeah, n pi x. So we will not have any c in the denominator. This c, this c, c, n pi x, n pi x. This is n pi x, n pi x. Now since sin n pi is 0 for every integer n, the first term will again vanish out. We will be left with 2 by n square pi square times integration of sine is minus cos. So minus cos n pi x by n pi 0 to 1. This is minus 2 by n cube pi cube. You know that cos n pi is minus 1 to the power n and cos 0 is 1. So this is 2 times 1 minus minus 1 to the power n by n cube pi cube. So from here we get En is equal to, this implies En is equal to 2 1 minus minus 1 to the power n by n cube pi cube answer from here. And the denominator term is 1 by 2, so this is 4. Also we have n pi c, again this is not c, n pi dn, n pi dn is equal to same as en, is equal to 4 1 minus minus 1 to the power n by n cube pi cube. So therefore dn is 4 1 minus minus 1 to the power n by n power 4 pi power 4. You can further see that for even n, en and dn will be 0, and for odd n, the en will be 8 times 8 by n cube pi cube. So this is equal to 0 when n is even, and 8 by n cube pi cube when n is odd, and this is equal to 0 when n is even, and this is 8 by n power 4 pi power 4 when n is odd. So I hope this solution was fine with everyone. I will just wait for 10 minutes so that if you have any doubt you can ask. So I hope this session was useful for you all, and I would like you to try similar questions, practice more and more, so that you get uh, more comfortable with these type of questions. If you have any doubt, you can always let me know. You can either mail me or comment on the YouTube video. So thank you so much. We'll meet next Friday, 6 p.m. again. We'll be solving some more questions related to the further theories that will be done in the theory classes. And I'm also hoping that you all are going through the lecture videos, because if you don't go through them, these sessions won't be that much useful. So the idea is to first go through the theory classes, then practice questions, then only it will be easier for you to understand why we are doing such calculations, where the things are coming from. Nothing is random. Every step that we are taking has some meaning, has some intention that we need to do. So I hope this session was fine. Thank you so much. We'll meet next Friday.